So for this video and this topic, we will primarily be covering inverse trigonometric functions. Now, in Miss Moshe's video, she gets more into how we derive the derivatives for our trigonometric functions, and I'll get into that for sine specifically, and then I will list all the trigonometric functions, and primarily I will show how to calculate both our derivatives and our integrals when using trigonometric functions. So the manner in which the derivative for sine inverse of x was discovered was through the use of Pythagorean theorem. So if we are going on the standard sine theta equation to equal x, then there must be a Pythagorean triangle which matches this. So in this case, the Pythagorean triangle that matches it is this triangle where we have x, 1, and this portion here. And what we must find essentially is this chunk down here, which we would discover through Pythagorean theorem to be root 1 squared minus x squared. So now you're probably wondering as to how this helps to actually find our sine inverse of x. Well, as we know, the inverse of any function is simply when you are switching the range and domain. And in this case, if our f of x is equal to sine theta equaling x, then our g of x is our integral. So in this case, it would be sine of x. And in this case, our g of x will be our inverse, which is our sine inverse of x. So now a fundamental thing to understand is that we're looking for the derivative of the inverse of sine of x. So to find that, it would be the derivative of our g of x. In this case, the derivative of our inverse function will be 1 over the f prime of g of x using chain rule. And in this situation, our f of x is equal to sine x as listed above. Addition as listed above, because it is the inverse, our g of x is sine inverse sine of x, or which is often called arc sine of x. And our f prime of x is equal to cosine x. So essentially what that means in this scenario is because our f prime of x is cosine x, we have to use our cos ratio from this triangle to find our denominator chunk. And once we ultimately do that, we will get our equation for our derivative of sine inverse x to equal 1 over, now our f prime of g of x using chain rule with our value of cos x as our f prime of x and our g of x as sine inverse of x will ultimately give us on our denominator a value of, using that ratios, will give us a value of root 1 minus x squared. Here, I'll rewrite the 1 minus x squared as our derivative for inverse sine. So now in the similar manner that we found the derivative equation for sine, there are the similar ways to find the same equations for cosine, tangent, cotangent, secant, and cosecant as well in regards to the derivative functions. But I'll simply write them all down as they are all necessary to know. Additionally, we also need to know the integral functions for many of these equations. So in this case, our derivative of inverse sine of x is 1 over the root of 1 minus x squared. Our derivative function for the inverse of cosine x, also found through the Pythagorean triangle, is negative 1 over the root of 1 minus x squared. For inverse tangent, or arctangent, you could say, our derivative is equal to 1 over x squared plus 1. Cotangent is equal to negative 1 minus x squared plus 1. Secant, inverse, or arcsecant, is equal to 1 over the absolute value of x times root x squared minus 1. Only one more left here for our derivatives. And finally, our derivative is for cosecant, or inverse cosecant, or arc cosecant, is equal to negative 1 all over the absolute value of x times root x squared minus 1. So now these are all of our derivative functions for our inverse trigonometric functions. And we can basically get into some examples now as to where these would actually be used in a derivative equation. So now, using the equations, which I had listed above, of all of our inverse trigonometric functions, we can find the derivative of a function if we're given such a function as here. If we're asked to take the derivative of arcsine of 7x. So now, in this situation specifically, what we would be using is chain rule. So firstly, what we would do is our f of x for inverse sine is obviously 1 over root 1 minus x squared. So as such, according to chain rule, in this situation, we would plug in which in this case, our g of x, 7x, we would plug in our g of x for the derivative of our f of x. So if our f of x is arcsine, then the derivative of our f of x is 1 over 1 minus x squared. And so plugging in our g of x for this function will give us 1 over 1 minus 7x squared. And then additionally, following the chain rule, we must multiply this value by the derivative of our g of x. And if our g of x in this case is our 7x, then that'll give us a value of 7. Our g prime of x would be 7, which means ultimately the value for our derivative in this scenario would be 7 over root 1 minus 7x squared. So that would be our final answer for our derivative of arcsine of 7x. So now, in addition to finding the derivatives of our inverse trigonometric functions, we're also tasked with being able to take integration in relation to our inverse trigonometric functions. So now, based off the derivative formulas prior, we can also find integral formulas for our inverse functions. However, for now, I'll just write down 3 central ones, which we will often run into. So the integral, because essentially it's just the opposite of our derivative, the integral of dx 1 minus x squared will be equal to sine inverse sine, so arcsine, plus c. The derivative, the integral of dx for x squared plus 1. Remember, once again, it's in relation to their derivative formulas. The integral of that function will be equal to tan inverse tan plus c. And then the integral of dx over the absolute value of x multiplied by x squared minus 1, as you might expect, as it's completely related to its derivative function, would be inverse secant plus c. So now, based on our knowledge of our integration functions in relation to our inverse trigonometric functions, we'd be able to answer this example here in regards to finding the integral. So with most of these, pretty much all of them with inverse trigonometric functions, what we have to use is u substitution. So in this case, what I would create to be my u will be 4t, and therefore my du will be, my du will be 4 dt, and because there isn't simply a 4 dt in the equation, we will divide out the 4 on this side, and we will get du over 4 to be equal to our dt. Now, specifically, if you're wondering the reason as to why I used 4t as my u value, is because as you see when I rewrite the equation, as soon as I looked at this, the first thing that I knew is it is based off the sine integral, the integral equation, or rather the derivative equation related to sine, because obviously we know that the derivative equation of inverse sine of x is 1 over root 1 minus x squared, and as such the integral of d of x over the root of 1 minus x squared is inverse sine. And so in this case, I simply was able to notice quickly that this matches the mold of our root 1 minus x squared. So in this case, we will now be in a situation where we will have 1/4 times the integral of du over root 1 minus u squared. And now, as intended, this will match our the integral function for our sine inverse, or arc sine. So now it will result in us getting 1/4 times inverse sine or arc sine of u, that is the integral for this function. And now we'll have to plug in for our u. So we will then finally get 1/4 times the arc sine of 4t plus c. And this will be the integration, or the integral value, for our integral of dt over root 1 minus 16t squared.